Okay, enough about me and Exploratory. Let's get started. Exploratory online seminar number 77, machine learning, build, test, and predict with Exploratory. Okay, so first off, I'm going to introduce what that data, talk about what really prediction model is. And then I'm going to move on to the grammar analytics, which I did the seminar before, but it's kind of briefly touch on it to how you can understand or interpret the prediction models. And then the last three pieces, the kind of main contents on this seminar, which is how you evaluate the models, really about the metrics, what metrics you can use. And then you test the models. And then last not least, you want to use that to predict for the data that you don't have the answers yet. Okay, so let's start with the prediction model basics. We have this kind of mapping. So these are each box represents each analytic type or algorithm. And these are the ones that's supported by Exploratory. There's maybe some of the other stuff also supported by Exploratory, but missed in this picture. But this is actually kind of important because sort of like you start from the at the center, the start box. And then from there, it depends what you want to do. These highlighted ones are something called supervised learning. So the not highlighted or kind of blurred one with those blues are called unsupervised learning. So today is really about the supervised learning, but what really supervised is basically like you have the answers in the data and you build the models, and then you want to actually predict for the data that doesn't have the answers. And then depend on what type of things you want to predict, and then you go to different models. So this map is kind of intimidating. So let's go to a little bit more simplified version here. So again, it's really about a target data, the data type. So if the data type is numeric, such as, for example, sales or maybe salary or something like that, then you want to go to the numeric side, and then there are various algorithms such as linear regression or random forest and so on. And then there's a green box is a statistical learning, and then purple box, purple text is machine learning. And then there are some difference between these two, which I'm going to cover that towards the end. But I want you guys to understand what the there are two types of machine learning or learning models. And at the center is if you have the data that you want to predict is a true or false type of data, which we call it logical data type. This actually happens a lot. For example, a conversion, you have the customers coming to your website and some of them convert, some of them don't. Or some of the customers quit, some of the customers don't quit. Some of the patients become ill, some of the patients don't become ill. So in this world, there are a lot of true false type of data. And in that case, you have these algorithms. And then there is a true false plus time. And this is a more like a survival analysis world, which I'm not going to cover in this seminar, but there's such case as well. But in either way, it's always there's a statistical learning and a machine learning models. That's one key point. The prediction model is really a formula or a set of rules that are defined by algorithms based on the patterns that algorithms learn or identify in the past data or whatever the data you give to the algorithm in order to predict future, not necessarily the future. It can be the past data, but that doesn't have the answers. So it's unknown data. Okay, so that's really the prediction model in a nutshell. So let's say we have the data that have answers, for example, income or sales or conversion status or something like that. And then we are interested in that particular information. Therefore, hey, we have the new data coming in. Can we predict those things even though that data itself doesn't have the answers? So we're going to use algorithms such as random forest to detect the relationships and patterns that can be found in the data, can exist in the data. And then based on that, we algorithm build something called models. And then once models are built, we can use that to predict the answers for the data that doesn't have answers. Okay. So use case, maybe I've been kind of covering this, so it can be kind of repetitive. But yeah, I'm not going to repeat this, but basically like you have the, conversion data, customer data. Some of them converted, some of them didn't convert, right? So that's basically you go through the same step and then build a model. And then eventually, hopefully, like you can predict, hey, which customers are high likely are going to convert and which customers are not going to convert. Then if with that information, you can focus on which sort of lead customers you should focus on or approach in a different ways. Okay, so here's the data, that's the customer data. And then the most left-hand side, conversion column, that's the column that we are interested in or we want to predict. And then we have other data. This is each row is a customer. So that means this age, time, country, so on. These are the customer attributes data. And then we want to predict this conversion based on these customer attributes. And we call it like the variable that we are interested in. We call it variable, but basically in the table format, this is actually the column. But we want to predict this conversion status based on the green squared information, which we call it predictor variables. Okay, target variables and predictor variables. So we give the data to the algorithm find the patterns in the data, and then build a model based on that pattern. Okay, and then what kind of model is that? So for example, it's a very simple case, linear regression. Linear regression is about the kind of draw the straight line in the middle of the data. So x-axis working years and y-axis salary. So maybe working years goes by, let's say 1 year and 2 years and 3 years, then salary in this company increase. And how much increase by the change of 1 year in working years? So that's happened to be $468. That's the kind of slope. And then this type of information is basically can be defined as a formula, salary equal 468 multiply working years plus 1,228. So this is like a formula, right? So this is the model. This blue line or that formula is the model when it comes to linear regression model. This is a statistical running model. Statistical running model usually, in most cases, I think maybe I don't want to use the all, but because there's always some kind of exception. But as far as I know, it's always the formula. Okay. As opposed to that, the machine learning model, it tends to have this type of a set of rules. Think of it as kind of like if else or if function in Excel. So in this case, for example, we have 100 people, and then let's say first if condition is salary is greater than 5,500 or not, that kind of stuff. So and then you're gonna build it's not you actually, the algorithm build this type of series of questions or if statement or conditions, and then this itself becomes the model. Okay, so this is the machine learning. So there's so difference there between machine learning and a statistical learning model. Either way, once you have the model, then you can feed the new data. In this case, the data doesn't have data that doesn't have the answer, and then the model basically the data goes into the model. The model will return the answer for each row. In this case, each customer. Okay, so that's really the nutshell, how the prediction model works. And then here's the grammar analytics. So once you build a model, typically, if you're super new to this prediction model or machine learning world, then you sort of expect, oh, hey, I want to create a model and then predict it, and then that's the end of the story. But in most cases in a data analysis world, you don't really build a model to predict necessarily. You build a model to analyze the data you have. So that says once you build a model, there are so many information actually contained in the model, so you can learn a lot about your data. So there are a bunch of things, a bunch of algorithms, and how you're going to learn, because in typical case, each model, each algorithm has a different way of understanding or provide a different output. But in exploratory, we provide this grammar of analytics, which is basically the framework for interpreting any type of analytics models or prediction models. So they're kind of like algorithm agnostic. So these are the four things: variable importance, prediction by variables, coefficient, and evaluation. I have done this seminar a few weeks ago, seminar number 75. So if you want to know more detail about this grammar of analytics or model agnostic interpretability for machine learning, please find this seminar. There's a recording available. You can go to our website and under the Learn, go to training seminar. Then you can find a seminar link. And then when you click it, then like in that page, like you can, maybe like you might have to click one more link or something, but then you're going to see like a series of the past recording. Okay. But in this seminar, I'm going to just touch base lightly or briefly. So first, variable importance. Variable importance provides you or help you understand which variables are more important than the others in terms of predicting the target variable. Or another way to say is which variables are more correlated or has higher degree of relationship with the target variable. And the next one is the prediction by variable. This view provides you, help you understand like how the target variable change when you move, when you change one of the variable. So for example, in this case, like in the first chart, the left-hand side top is like job level. What happened like with job level change for one level from 2 to 3 or 3 to 4, like how much would in this case, monthly income will change. So that type of thing, so you can understand that like each relationship of all the variables. The next one is the coefficient. So this one is available only for statistical learning models. So like if you're dealing with machine learning models such as random forest, XGBoost, decision tree, and so on, then you don't have this. This is really statistical stuff. So then obviously it gets a little bit complicated if you're super new to this thing. However, it's not two things that are important. It's really how much you would change in the target variable when a given prediction variable change in one unit. But that information was sort of like, hey, you just said like you can find some information like that in this prediction by variable. Yes. So having said that, you don't really need to go to coefficient to get that particular information, but there's another information is called the significance. So significance is really about that change, the change that I was talking about, basically the change in the target variable when a given prediction variable change in one unit. That change is significant or marginal. Is that something that we should pay attention or not pay attention? Because if it's not that much of the difference, then like why we have to spend so much time for like even like digging further and stuff. So this view really help you like which variable more you can be more confident in terms of like spending more time analyzing that relationship with a given variable against a target variable. And so that's the coefficient view. And the last one is the evaluation. And this is really the main topic for today. So evaluation, like you go to the summary view and you can see like these bunch of metrics, which is kind of confusing. So that's the topic that I'm going to go into a little bit further. Okay. So to this seminar, I'm going to focus on these two things, numerical, logical. These are the two types of target variables. Numerical meaning, so like you're trying to build a model to predict like sales or number of orders or something like that, something about the numbers. Logical is a true or false, converted or not converted, becomes ill or didn't become ill, something like that. Okay, so for these two types, and then underneath each has two types of algorithms, right? So one is the statistical learning and then the other machine learning. Either way, you can use the same metrics to evaluate the prediction quality. Prediction quality is really about how accurate this prediction model if we use to predict. Actually, that word is actually can be misleading, but at this point, I'm gonna use that word for now. Okay. So next, so there are two types, right? The numerical data type as a target variable, and the other one was a logical data type as a target variable. So let's start with the numerical. Numerical case, like there are two type of metrics. Obviously, there's a bunch of more, but I think these two are really good starting point. Most of the time, like I think these are good enough. First one is the R squared. This is used a lot, and this is not just for the prediction, but it's really when you're building a model, it's really useful one. So this one is it ranges between 0 and 1. 1 is the highest. And basically 1 meaning is that it's really the data is sort of perfectly sort of correlated between the target variable and then the predictor variables. So what that means, it indicates how a given variable can explain the variance of the target variable. Wow. So this is like if you're familiar with it, it probably makes sense. But if you're not, then what the value, variance, right? So let's take a look at these two pictures. I don't have enough time in this seminar, so I can't really go into the detail. But this picture might give you a better idea. So left-hand side, when the R square is high, maybe it's like close to 1 or something, then you build a model. And this is a very simple case, right? So, but the center, the blue line is the model, and in this case, the linear regression model. Okay, and then all the dots are actually in this case maybe like employee or customers or whatever that each row. Okay, and then those lines are kind of like surrounding the blue straight line, right, left hand side, and then the red line is an average or like a mean. So in this case, y-axis is income, and then that means that this orange red line is the average income. Okay, so compared to the average, because average doesn't really explain this company's the income variance. Variance means kind of distribution, right? So it's not really explained because only area that average is describing is the people with the 15 years of working years. X-axis is working years. Okay, but other than that, like beyond 20 years or less than 10 years, it's like average is really not saying anything about it. However, when you use this prediction model, the blue line, and then this one is actually very close to all the employees, right? So even like 25 years, 30 years, or 5 years of working years, it's always a kind of like sort of predicting or indicating that each employee or most of the employees' salary. It's not exact, but it's very close. But compared to that, right-hand side, R square is low. This is probably like R square is closer to 1 or something. And then this blue line is basically the linear regression lines goes in the middle of all the data. And then compared with against the red line, which is the average or mean, and it's not much of a difference, right? So that means just like a red line, even with the blue line, which is a prediction model or linear regression prediction model, it's not really helping me understand the variance of this like the employee data, because all the employees are kind of going everywhere. And I don't know like what's going on. Like even it doesn't really matter if it's 40 years or 25 years or 30 years. It's like anywhere you go, like it's always like salary or income ranges from 0 to 120K. It just doesn't really helping me. I'd rather maybe just use the average or something, right? Like 35 years or 40 years, and it's always I can tell just give it an average value, then it's not too bad. So that says, R square is really giving you an idea how much this linear, this prediction model is helping. And when I say helping, it's explaining the variance of the data. And then if that number is low, closer to 0, that means 0 is basically the average, average line, the red line. So how closer to the average? Okay, so that's really a nutshell or kind of visualized way of explaining R squared. But again, R squared indicates how the model is fitting the data, or how much it can explain the variance of the target variable. Okay. In RMSE, this also can be used often for evaluating the machine learning models or the statistical learning models. It's really a mean of differences between the actual values and the predicted values. So smaller is better. And there's no range. This is really the average of difference. In the last case, we are looking at the salary or like income. So that means average salary difference in difference. So for example, here RMSE, by the way, RMSE stands for root mean square error. Error is a difference. And then you square, and then you mean, and then you root. So that's kind of like how you calculate, how creative way of naming this metric. But nonetheless, so it says 1,110, this case is $1,110. And then we can interpret this as the predicted values are different from the actual values for about $1,110 in average. And then we visualize it. So it happen to be like we have the predicted values and actual values, and then we just draw the scatter plot. And then seems like at the center is kind of dotted line. It's kind of a gray line. That's the linear regression model. However, all the blue dots, those are each employee, right? They're not on the dotted line. And of course, it's never be on everybody on the same line. So like how much of the difference? And then that 1,110 is actually the average wise, this much, there's some kind of, this much, there is a gap between the actual value and the predicted values. So this kind of a blue colored belt area. Okay. So that's RMSE. So these are two things, and these two things are actually different, but at the same time, you never have like, hey, somehow R squared is high, but RMSE is low, or vice versa. It's always when the R squared is high, then RMSE. Sorry, I think I said something wrong. RMSE, you want the RMSE to be low, and you want R squared to be high. So therefore, you have the R squared high and then RMSE low, but you never have like somehow R squared is high and then RMSE is high. That kind of case. So those two are basically correlated in a kind of negative way. Okay. Then if you're doing like analysis, basically, like if you have to pick one, like I would go with R squared. That's more useful in terms of like even analyzing, because at the end of the day, another thing is great thing about R squared is you ranging from 0 to 1, and you can say like, oh, closer to 1, that means it's good. It's closer to 0, that means it's not. It's very intuitive. RMSE, like if you get the RMSE 1,000, what 1,000 really means, right? So you have to compare with another model, or like, the creator with a different algorithm, different combination of the variables or something. Then another model is producing RMSE is like 1,200. Then you can say, oh, okay, the model with 1,000 is better because, again, RMSE is the average difference, right? So anyway, so those are the two metrics. And the other one is a logical, if you're predicting the true false. And then this is where like you want to use AUC. AUC stands for area under curve. I'm not going to go into the detail in this seminar, but you can see under the summary tab. And then this is basically a metric that indicates how much a given model can separate true data and false data. For example, let's say like you have like a converted customers and a not converted customers. And then basically what you want to find is like what makes the difference, those two groups. And if you happen to have those data, those attributes in the data, then the model can build algorithm can build a model to separate those two groups, right? But sometimes it's not, this world is not that simple, right? So like even though you have the age, you have maybe, lengths they use a product or something like that. But if that have nothing to do with the probability of this customer is going to convert or not, then this AUC score is going to be low because it's not going to help you to predict better. So that's really the nature of the AUC. AUC values ranging from between 0.5 to 1. 1 is the strongest. Okay, so the more intuitive way to by visualizing this data is you go to the probability tab, and you can see like a true data and false data distribution are separate. They can kind of different mountains, but when the AUC is low, you have this data kind of like in the same way. It's almost like overlapping each other. Nonetheless, those are the evaluation. However, there's one problem here. Before going there, like let's build the model first, right here. So we have this employee data, 1,470 rows. That means we have 1,470 employee. Each row is employee here, and then all the attributes. And then let's say we have this like attrition, which is basically has a true or false. So we want to build a model to be able to predict, hey, a given employee is going to quit or not, right? So that kind of model that we want to create based on other information. Let's just hypothetically say maybe like age is old people like tend to quit or less quit, or maybe like a male tend to quit compared to female, and so on. Okay, so we go to the analytics, and then let's create the first model. Let's say like I'm going to use a random forest, and then target variable, and then I'm going to select attrition, and then predictor variables, and I'm going to select all of them except this date, start date, end date information. And also I'm going to remove this department, because department and then job role, those are actually the same kind, similar information. It's kind of hierarchical. So each department has a specific job role. So like that means if you know the job role, you know the department. So that you don't want to have like the variables who are related to each other or correlated to each other. So I'm remove that. And then also this monthly income is also, I already know this data that this one is very correlated to job level. In this company, turned out, depends on the job level, you can kind of know like how much the salary range you're going to be. So I'm gonna, I deselected monthly income. Okay. So at this point, like I have 21 columns that like, I don't really need these 21 columns, but in this demo wise, I'm gonna just select all of them and then click OK. And then let's build a model. And like I said, like by using a grammar of analytics, really you go to the importance to see which variables are important, and then prediction to see like how the change of the attrition probability by the change in overtime and job level and so on. But here today, we want to see go into the summary. This is where you can see, you can evaluate the prediction quality. And here's the AUC 0.96. And then I don't know if you remember or not, but this one ranges from 0.5 to 1. 1 is basically 100%. It's like you can't expect anything better. Okay, so the very close to 1, 0.96. And by the way, this area under curve, this curve, where the curve is coming from, that is this something called ROC curve. So ROC curve, you can see the visual representation of that curve. And then briefly speaking, this curve is kind of a zigzag, but just try to see as a curve. And then when the AC is 1, then this blue line straight up to here, like a 1 area, and then go all the way. So it's a square. So that's the best case scenario. Then you never get that 1 unless you have a kind of weird simple data. So that means it's always this one is kind of like a curve. And then this time we have like AUC 0.96. This is almost like a 96% of like entire this kind of square area. Okay, so nonetheless, we have the AUC here and other metrics too, but today we're going to just focus on the AUC. And then now here's that bad woman. So far we have built a model, and then they evaluated the prediction models against the original data that prediction model is very familiar with, what that means. So that's the next topic. So test modes. So we, at the beginning, like I explained, like, this is how you build a model, behind the scene in a way. So you have the data and give that data to algorithms find the patterns, and then based on the pattern, it builds the model. Now, once you build a model, then now you can give that new data that doesn't have answers, and then have the model predict and then return the answers. However, so far, what we have been doing is something like this. We got the model, that part is okay, but we didn't give the new data. So how you can even where did you get those like AUC or those metrics? Well, behind the scene, we give this original data to model as if this is a new data, without that target variable, which is the conversion. However, the data has a conversion column, but nonetheless, give the data to model, and the model using the other variable, the predictor variable, such as age, and then in this case, we have been using for the demo, age, and then job level, and then job role, and working years, and so on. And then based on that, each employee information, it returns the result, can be true or false. This case, like we are doing a logical variable, so it really the model is returning the probability of being true, but nonetheless the probability and also the true false type of information. Okay, and then how you calculate those AUC, or if the target variable is numerical, how you calculate those R square or RMSE? Well, we compare with this original data. So this is a weird scheme, right? So you use this data on the left-hand side and build a model. And then you use that same data back to the model, have it predict, and compare against the original data. It's sort of like, hey, you already know the answers. That I can do that. I don't need a machine. So, but that's what's really happening. And obviously, this is the model is based on built based on the pattern in the data. So it's not going to be, able to produce like 100% result, even though the model has seen the answers. That doesn't mean model is going to be able to return the exact same answer, because model is really the representation of the pattern in the data. So like every single employee doesn't fit the pattern, right? So you never get the 100% answers, but not still like it's sort of like not really fair. So ideally, we want the model to capture the patterns in the data that can be used not only to predict for the past or the known data, in this case, that the data that being used for the algorithm to build a model, but also for the future, the data doesn't have the answers. So that says we want to evaluate the prediction capability of a given model, in this case, a random forest model, with the data that the models haven't seen, that's the typo, haven't seen the answers yet. The data that the model was not built on. So what that means? This is actually it's pretty simple answer. So you have like 1,000 employees, then split the data into training data and the test data. Training data, let's say like 70%, 30% split or something. So like that means the training data has 700 employees and test data has 300 employees. And then using that training data to build a model. So at this point, this model is slightly different because it used to be able to use 1,000 employees data, but now it's down to 700 employees. But still, you can still build a model. Then once you have the model here, this point, we pretend like the test data, 300 employee data, as a new data that doesn't have answers. Even though there's answers, but from model's point of view, there's no answer, or model doesn't know the answer for this test data yet. So give this 300 employee or test data to the model and have model to predict, and then you get the prediction result. And from here, compare these two, so prediction result and original 300 employee data. Because cool thing about this 300 employee training test data, there is an answer, such as maybe income, or in this case, in our demo, attrition information. So we can kind of have those two and then see like, they are matching or not matching, how far, and so on. Okay, to do in Exploratory, you can actually use something called test mode. And then when you switch to true, default is false. And when you set to true, then exact the same thing like I have just shown in the slides is about to happen. So let's see like how that works. So go back to Exploratory. And then so far, this is basically all the things we're looking at is against the training data. And then we want to do the testing. So click on this config and then scroll all the way down to the bottom, the evaluation section. So this one, we can switch to true. That means test mode, and click apply button. And then behind the scene is split the data. You can change that like a ratio of testing and training. Default is 7:3, the 70% of the training. So now here you can see that there are two lines, one is the training and test. So it still does evaluation against training data, but also now it against the test data as well. And then how that data has been split, that is here, number of rows. So basically 1,029 out of 1,470 is reserved for the training. And then the rest is the 441 was reserved for the testing. And then basically this model predicted for the test data and then compare the predicted values and original values and then come up with this AUC. You notice this, as you notice here, is that AUC used to be like 0.96. This numbers might slightly different because previously, like when we built, we had entire data. So the number might be different, but nonetheless, it's very close, like 0.96 something, and it's pretty good. However, when you see the test, here's a 0.80, like 80% of the best, the one is best, and then compared to that, like 80%. So what happens? So it's like there's a huge difference here. And then you can visualize this difference by going to the ROC curves. So like I said, like basically AUC is the calculation values of this like ROC, like area under the curve. What is the area, sort of like ratio of the area under the curve. So orange is the training and the test is the blue. So you can see like how degraded that testing, data prediction quality is compared to the training data. And that's the difference. So what's really happening here? Another thing, in order to explain, like I want to create this logistic regression model, which is statistical learning model. So this random forest is a machine learning model. And so let's compare with the statistical learning model because that will give you a better idea like why there's a difference like this. So I'm going to just duplicate. Okay, and then I'm going to just name it logistic regression. And then only thing I'm going to change is this algorithm type from random forest to logistic regression. And the other stuff is the same. Target variable, predictor variable, exact the same. And then I'm going to just click run. That means that even the setting under the config setting is also the same, which is still the test mode. Okay. So you get this type of things, and then like I'm going to go to the summary. And this basically gives you the AUC values and so on. And as you notice here though, so AUC is training and test, and both of them are similar numbers, like 0.85, 0.84 is pretty much the same numbers. So compared to the random forest case is against the training data, 0.96 is really good, but then the test data is not that much. Logistic regression, the training data is not like so too good, it's not like very good. However, there's not much difference between training and test. And this is where the difference between these two type of model actually comes in. So it's really a machine learning and a statistical learning difference. So left-hand side, statistical learning, maybe like linear regression. This time I was using logistic regression. And then machine learning, right-hand side is a decision tree and random forest and so on. And then, so there are some differences. And then main difference, one of the main difference is here, the nonlinear relationship. So statistical learning models, because the nature of the statistical learning is to use the formula. Not even a nature, it's just the foundation, like mechanism of the statistical learning is using the formula. So therefore, it cannot really change, it cannot be really flexible to fit with actual data, right? So however, machine learning side, the simple example is the decision tree. Like basically the series of conditions or like if condition. So that means, think of it like, for example, like working years, x-axis, and then y-axis is the monthly income. And then the gray line is the actual values, okay? So like it's the total working years, and then like each year, like we just calculated the average of the income. Okay, so then we draw the line, that's the gray line. And then the linear regression lines basically draw this blue straight line, because if it's straight line, like you can, represent as a formula, it doesn't have to be straight. For example, linear regression is not straight, it's like a curve. However, if you have the formula, there's always some kind of a constraint. So the constraint prevents you from fitting the model to the data in a very flexible way. However, random forest, there's no such thing. So therefore, total working years up to like, let's say this actual data up to like 20 years, it's kind of like going up. But then from 20 to 21, I don't know what happened in this company, but somehow the income goes straight up. This is the average though, but still it's straight up. And after that point, that it's not like a income keeps going up. It's almost like it doesn't matter if you're 25 or 30 years, 40 years, it's pretty much the same. So obviously that means working years is not really the important factor, maybe something else. Right, so the trend has changed. Like a trend is like going up and then straight up and then doesn't change. However, that kind of relation, that kind of pattern cannot be captured by a statistical learning model. There's always exceptions, so please don't challenge me. But in most cases, the statistical learning model is not good at it. So the left-hand side, as you see, the blue line just straight. So this is a linear regression case, but logistic regression, which is to predict the logical value true and false, but that's also the same thing. So that means if you want to predict with only this, whatever the one that we are looking at right now, random forest can predict pretty good predicted values, which is super close to the actual values for all the employees. Compared to that, linear regression is like it can be good for certain people, but not all of them, right? So that basically produce this type of difference. Okay, so that's why like logistic regression, AUC doesn't change, and then the first of all, for even the training, it doesn't give you the great quality. However, because of that constraint, the pattern you can find the training data and the test data in this case is coming from the same data set, so it's not much, there's not much of difference in the first place, but pretty much similar. So like you use the same model to predict for the training data or test data, you get the same kind of quality, same kind of prediction score, the same kind of result. However, random forest, even though the training data and the test data is pretty similar because it's coming from the same data set, however, there's some differences. And then random forests learn too much. Some maybe a little bit of difference, happening, but that's not really a global trend, but it's kind of like localized, maybe like only happening in this particular given 10 people or something. But random forest catches that pattern and then define it as an if condition and behind the scene internally, and then use it. So therefore, it can produce a good quality of prediction for the training data, but that doesn't mean those 10 people don't exist in the testing data. Therefore, when you try to predict for the testing data, it doesn't provide the good quality of the prediction. So you can see that difference in a very clear way with this ROC curves, logistic regression. Again, test data and the training data doesn't produce much of the difference. So in general, machine learning models can be more flexible and fit the training data better. This makes machine learning models prediction quality better than the statistical learning models when they are tested against the training data. And sometimes we call it like overfit or some, I think, overlearning, overfit or something like that. But anyway, it's fitting too much. But in general, however, since machine learning models can overlearn the training data, they might not produce the same prediction quality when tested against the unknown data, such as the test data. On the other hand, statistical learning models don't produce much difference between training and test data set. And this knowledge is very important. I'm not sure this is even knowledge. It's information. This information is very important because that said, when you're using a statistical learning model, you don't really have to worry about like, oh, am I testing the test data? Or am I testing against the training data kind of stuff? Because pretty much the same. But when you're using a machine learning model, then you got to be careful because there's this kind of thing tend to happen with machine learning model. Okay. So, and then, but another thing is though, is that at the end of the day, what you're trying to do, if you're trying to predict, you not just like analyzing the data, but like, hey, you know what, like I want to use this model to start predicting. And in that case, you want to do the test mode and see like if you use this one and start predicting, then what kind of result you're going to expect, right? So that part is important. But then again, the machine learning model, you're trying to use that to predict and make sure you use the test mode, and then what you have is going to meet your expectation or not. Okay, so that's the test modes, and the next one, the last one, is a predict with models. So we got the model so far, and then this is what we wanted to do. So we want to give the new data that it's not test data. It's brand new. It's like a completely, come from different place. However, it's not completely different things, right? If it's completely different data, then when you try to predict, you get some kind of like random result. So obviously, like, it's just that like new employees, for example, customer case is like a new customers. You expect the trend tend to be similar. Unless some kind of like historical thing happened, like before the COVID and after the COVID or something like that. So, but you don't have answers in that data, so you want to predict. So you can actually do it from the exploratory here. So let's see, pretend like here, I have imported beforehand. This is like 100 new employee. Okay. And then this data happen to have the answers already, but let's pretend like we don't have this column. And then, but we want to actually use the model that we created under this data frame, employee data English data frame. And then we want to use that like either random forest or logistic regression to predict each employee's probability of being true. Okay, so for that, you can actually go from this add step plus bottom, right-hand side top, and then select the predict with model bracket analytics view. And then here, you can select the data frame where you build the prediction model. So like I created this under the employee data English. And then which model you're talking about. So like here, like I'm going to use a random forest for now, and then click run button. And then you get the predicted result here, the predicted label, predicted probability. Again, this type of prediction model return the probability for when the target variable is logical, true or false. Then here's the false and true is based on the predicted probability. The default here is that like cut point for true and false is 0.5 you use. So if any predicted probability higher than 0.5 or greater than 50%, and it ended up becoming true, otherwise false. You can change it, but a default is 0.5. So you get these two as a prediction result. Okay. So that's really the prediction. It's basically the same thing for linear regression, XGBoost, decision tree. The pattern is basically the same. For the statistical learning model, you might have extra outputs, something like a standard error, confidence interval, and so on. But basically, like you get the predicted probability and predicted label for the case of the target variable being logical. So that's the prediction. But sometimes I get the questions, hey, like this data, I actually wanted to use the model to predict, but for some reason, I have answer. This is a new data, but I have an answer. And I want to see, because the model that I created was like, let's say like a few months ago, but I want to see like that model is still valid with the data I have today. Right. So in that case, you can actually evaluate. Let's say like you want to see like AUC, like AUC is still as good as we expected or we thought. So in that case, you can actually do it as long as you have this predicted probability column, and then like you have this like original sort of like answer column. In this case, attrition. So how you do it? So from the predicted probability column head up menu or the plus button, either way. So let's go from this column header menu. And at the bottom says predict bracket analytics, analytics, the second from the bottom. And then in the sub menu, way down here, evaluate quality of prediction. And in this case, the result is actually we are doing something called binary classification, really is about like a logical column, true or false. So the two ways to evaluate, one is metrics, and that's what we want. The other one is, it says ROC, basically produce the ROC data to draw ROC curve. This time, like we want to do like metrics. So select the metrics, and then probability column, so predicted probability, that's fine. Actual value column, that's wrong, not the age. So this one is like we want to select attrition. Okay. And then, so basically, AUC can be calculated by comparing the predicted probability against the answer column, in this case, attrition. Okay. And then threshold value, you can just set that like 0.5 or use optimal value. But this part doesn't really matter as long as you're calculating AUC. AUC is not impacted by this kind of threshold at all. However, if you happen to know F-score, recall, and precision, and so on, then this threshold matters. And in that case, you can actually select use optimal value for some metric that you're interested in. Either way, so like I'm going to just go round bottom. And then this is the result that you get basically based on the prediction result against the answers of this data. And then like I get like 0.87. And then like we see here, it's sort of, this is kind of expected because you remember like when we built a random forest, the training data was like 0.96. However, the test data was, way down 0.80. So, probably like somewhere around that. And then like this new data case happened to be 0.87, which is actually not bad as the testing data we saw. Okay, so that's the how you evaluate after you do the prediction with the model you created under the analytics tab. Okay, so that's it for today. So we covered today is basically these 5 things. So what the prediction model is, and grammable analytics use that to interpret the models. And also, like now evaluating the models, we talk about 2 types of models. One is the numerical, and the other one is logicals. So numerical target variable case, we have the R square and RMC. And then logical target variable case, we have AUC. No, those are not the only metrics, but I think those are the pretty major. Wherever you go, you always see those those metrics. And the reason was not random because those are very useful one. And then like you have that, but make sure, especially the machine learning model case, make sure like you use a test mode to see any difference between the training and test, so that make sure like you don't get over excited just because you get 0.96 against the training data. And then like once you have the model, most of the time like that's the kind of end of the story. But sometimes like, hey, looks like a model is stable, data is stable, then like I want to actually start using it. In that case, you can use that model to predict for new coming data. Okay. And that's it for today.